Hello everyone, this is Martha from the Academic Support Center once again. This is going to be a video for Stats 2. It's going to be a quick example of the steps of computing beta. Now beta is the probability of a type. Alright, so the first step that we have to do to compute the beta is computing this x bar. And this is kind of an overall x bar, so that's the first thing that we do. So first is we compute the x bar, and the second thing that we're going to do is we're going to make a table. And in this table we have possible true mu's or true means, true population means. So let's get started. To compute the x bar, you take the hypothesis mean, which for this example is 18, and you subtract away the alpha, the z-score for the alpha. Now the z-score for a 0.01 alpha level is 2.33 rounded to 2 decimal places. So that is 2.33. We multiply that z-score by the standard deviation over the square root of n. Our standard deviation has been given to us as 4.2. Then we divide it by the square root of 45. Now if we take 2.33 times 4.2, we get 9.786. We divide it by the square root of 45. That gives us 18 minus 1.4588 and some more decimal places. Now when we take 18 and we subtract away this kind of margin of error that we've used before, we get a x bar of 16.54. And we use this same x bar for all of the possible mu's. Alright, on to the second step of computing beta. In this step, we make a table with all of the possible true means. We then compute the z-score. We look at the probability of type 2 error, and then the power, which is 1 minus beta, or power, sorry. So to get the z-score, we use the same formula that we've been using where we've got x bar minus mu over standard deviation divided by the square root of n. Now we filled it in for this table because with each possible true population mean, we use that same x bar that we computed previously. So we take our x bar 16.54 and subtract away 15.5. And then we divide that by 4.2 divided by the square root of 45. I have kept it in the number for the rest of the table, so I just put 6.261 rounding, but I kept it written out this way just as a reminder of what we were doing. So when we compute this out, we get a total, we get a z-score of 1.66. From here, we then go to the table. And so we're going to look at that table, or we're going to find that on the table. And that's the area under the curve, so we're going to go to 1.6 here. Then we go across 0, column 1, column 2, 3, 4, 5, 6. All right. Now, the area under the curve associated with a z-score of 1.66 is 0.9515. For the following z-scores, we won't be going back to each table, we'll just be filling out the table, but just remember that each time we compute a new z-score for each possible true mean, that we come back to this table and find it. So if we had a z-score that we somehow computed and we got 2.53 for our z-score, we come down to here to 2.5. The first column is 2.50, 2.51, 2.52, 2.53. That would be a 0.9943. But this is what we got, this 1.66 with an area under the curve of 0.9515. So let's go forward with that. So then we take that a z-score with the area of 0.9515 for our probability of a type 2 error, which is beta. we take 1 minus 0.9515, and that equals 0.0485. That is our beta. Now our power is 1 minus our beta. And with our power, it's 1 minus our beta, or the area under the table. So that is 0.9515. Now we're going to, for the rest of the video, we're just going to go through the table and do each calculation. So if we have a true mean, a true population mean of 15.75, that's our next one. So let's look at that. We take our x bar, 16.54, and subtract away our mean, or our true mean, of 15.75. Divide it by 4.2 divided by the square root of 45, or 6.261. That gives us a z-score of 1.26. Now, if we go back to the table, we would look, and that the area under the curve associated with a z-score of 1.26 is 0.8962. And that's the same as our power, so 0.8962. Now to get our beta, we would take 1 minus 0.8962, and that equals 0.1038. All right, so we're making progress on our table. Next, we've got a true population mean of 16. So 16.5 minus 16 divided by 6.261 gives us a z-score of 0.86. Now if we go to the table, the z-score, the area under the curve associated with that z-score is 0.8051. I'm just going to put that over in the power column, just to be quick. Now if I take 1 minus 0.8051, that gives an answer, or a power, or a beta of 0.1949. All right, we're making progress on this table. Let's do orange. Now if the true population mean was, say, 16.25, it would be 16.52 or 54 minus 16.25, all divided by 6.261, which is our sigma divided by the square root of n. That gives us a z-score of 0.46. The area under the curve from the table associated with this z-score is 0.6772. So I'm going to write that over here, my power, 0.6772. If I get my beta, I take 1 minus that area under the curve, 6.772, and the result is 0.3228. All right, moving right along. If our true population mean is 16.54, and we subtract away 16 and then do the division, that gets a z-score of 0.06. Why do you think it's so close? Now the area under the curve associated with the z-score of 0.06 is 0.5239. So we're going to write that over here with a beta, 5239. 1 minus 0.5239 gives us our theta, and the answer is 0.4761. All right, just 2 more for this example. Now what if our true population mean is 16.75? We take 16.54 minus 16.75 divided by sigma over the square root of n. That gets us a z-score of negative 0.34. Now the area associated under the curve for a z-score of negative 0.34 is 0.3669. So we're going to put that over here for our beta, 0.3669. And 1 minus 0.3669 equals 0.6331. Last one for this example is, what if our true population mean is 17? We take 16.54, subtract away 17, divide by sigma over the square root of n. That gets us a z-score of negative 0.73. The area under the curve associated with that z-score is 0.2327. 0.2327. 1 minus 0.2327 gives us a beta of 0.7673. Now it's important to understand why this matters, and we can do another video on that, but sometimes the steps of computing beta can be tricky. The steps are to calculate that x bar, we use that same x bar and we kind of compare it against each possible true population mean. Hope this helps. Have a great day.